Well, welcome. Good evening. It is so wonderful to have you here on this balmy March night. My name is Dr. Jessica Joustra, and I serve here as the director of our Wolter Center for Christian Scholarship. And I am just so grateful that you are all joining us here today for our final installment of our Wolter Center lecture series for the 2025-2026 academic year. This is our lecture in the natural science and mathematics. So welcome to you all. Here at Redeemer, as so many, if not all of you know, we confidently proclaim that God's work in the world, in his original creation, in Jesus' life, in his death, in his resurrection, in his coming restoration, that is a comprehensive work, one that stretches to every nook and cranny of God's creation. It is, to use the words of one of my favorite theologians, and I know many of you have heard this quote before, but that's okay. We'll hear it again. The gospel is a joyful tiding, not only for the individual person, but for humanity, for the family, for the state, for society, for art, for science, for the entire cosmos, fitting for today, for the whole groaning creation. And these lectures are just one part of the work that the Wolter Center does in proclaiming and excavating and applying that good message. These lectures and the work of the center as a whole seek to faithfully steward the good gifts of the tradition upon which Redeemer stands, one that's been handed down from one generation to the next, proclaiming God's good and all-encompassing work, helping us think about how to live faithfully in God's good created world. So in all of our work at the center, including these lectures, we want to excavate and explore the way the gospel pulls us, shapes us, fashions us, directs us towards God's will and God's way in his world. So we ask questions like, what does it look like to witness to the lordship of Christ in our study, in the sciences, in the humanities, in the social sciences? How do we affirm the ongoing good of God's world while rejecting the twisting and distortion of sin? How does a Christian proclamation of who God is and how God created and how God will redeem affect how we think about any and every discipline? So one of the gifts of the center is that we have wonderful resources for thoughtful, reformed Christian scholarship. We have that for all the disciplines in our university through faithful teachers and scholars, not only that join together from other institutions, but also in-house. And in this lecture series in particular, we have our in-house specialists, what we call our faculty fellows, who join together with leading scholars outside of Redeemer to help us think through these central and difficult and really important questions. So we have fellows that invite these thinkers because they've helped us curate a wonderful list of people who can help us learn and discern well. So it's my pleasure tonight to first introduce you. We'll get to the main event very soon, planets, but to first introduce you to our Wolter Center faculty fellow in the natural sciences and mathematics, who's our in-house expert, Dr. Joel Klink, who will then introduce us to the theme and our speaker for tonight. So please welcome Dr. Klink.
Thank you, Jessica. So my name is Joel Klink, Dr. Klink to the students here. And it's my privilege to introduce our Wolters lecturer for this evening. So it's my great honor and privilege to welcome Dr. Channon Visscher from Dordt University to Redeemer here to give us this talk. So Dr. Visscher serves as a research scientist at the Space Science Institute, which is a nonprofit organization that is goal is to educate and further research on things of space and beyond that, perhaps. And he also serves as a professor of chemistry and planetary sciences at Dordt University in Iowa. His research is in an area that explores chemistry and physics of planetary atmospheres and the formation and evolution of planetary systems. In many ways, his work bridges the very, very small with the very, very large, as he studies molecules to planets and things like that. After completing his undergraduate degree at Dordt University, he earned both his master's and PhD at Washington University in St. Louis in the Earth and Planetary Sciences department there. And he went on to do postdoctoral research at the Lunar and Planetary Institute in Houston and the Southwest Research Institute in Boulder. He joined Dordt, I think, 13 years ago and has been serving there as a professor since then. Much of his research focuses on the modeling of dramatic events like the formation of the moon and planets and such things like that. In addition to his scientific research, Dr. Visscher has also been actively engaged in conversations about relationships between science, theology, and other academic disciplines. He has participated in the Bridging the Two Cultures of Science and Humanities program, hosted by the Scholarship and Christianity in Oxford, and he has recently co-authored a book, Science and Religion, Perspectives Across Disciplines, which I think he'll draw on from this evening as well. So tonight's lecture is entitled Creation Stories for Planetary Systems. And so we're looking forward to hearing some of these stories from Dr. Visscher. And it's we're very grateful that you've joined us on your reading break, and we appreciate your time here. So welcome.
Well, thank you so much. It's really been a blast today talking and meeting with you all. I've never been to Redeemer, and I feel like it is, I was going to say it feels almost overdue, but that seems to imply that, you should have invited me. Maybe you should have. No, I really do appreciate it. It is really, honestly, my privilege to be able to meet with you here. And yeah, greetings from Dordt. I know there's a lot we share in common, and I really do see you as our brothers and sisters in this type of work that we're doing, of really trying to embrace two things at once. Take very, very, very seriously the fact that we live in a created world, but we're doing so as followers of Christ. And so what does that look like for us if we take both of these things as seriously as we can? What are some of the things that might emerge from that? So I'm going to tell a few stories tonight, but I want to kind of frame this first and raise some questions. I will be raising more questions than delivering answers, and that's I'm going to just tell you right now that is a feature, not a bug. And so if you come away from this with more questions than answers, you're welcome. So I am really grateful to the series and to the Wolter Center, because I say this especially as someone who grew up in the tradition, but had never really learned how to articulate it in a particular way until a young student at then Dordt College was handed this little book and read all about reformational worldviews. And I can honestly say this had a profound impact on how I viewed the living out of my faith in all areas of life, as we like to say at Dordt. And I'm going to be really exploring one of the main themes of this book highlighted here. I would like to claim that was my highlight, but I'm pretty sure I bought this book used. And to be completely honest, this is not in my notes. To be completely honest, I remember being kind of annoyed by the highlighting, because I don't personally highlight books using a highlighter. I use pen if I'm going to highlight on margins. But this is a good location for a highlight. And so this is one of the themes that really hope to unpack further tonight. This notion that creation is indeed revelatory. And if it's revelatory, it imparts knowledge. And an implication, to quote the book again, that means that creation is knowable And so if that's the case, we inhabit a cosmos that is both contingent and comprehensible, an expression of God's wisdom and love and faithfulness. And so what we can do is unpack some of the implications of that. And two here that I'm going to be sort of drawing from tonight are first, this idea that if indeed creation is revelatory, it's serving as a witness to itself. And in fact, we might even say that objects in creation, by their very existence, there's a sense in which they are testifying to their past in some way. And if that's the case, then scientific inquiry becomes a way that we're trying to read the text of this creation, this text that the Belgic Confession says is laid before our eyes as if a beautiful book. And so further questions come. How faithful are our scientific descriptions of the world? Or to put it another way, I guess, how good is our translation of that text as we're doing this work? And could we even go so far as to say that scientific inquiry could actually yield genuine insight into the order of what has been created? Right? And I'm drawing here, of course, from your very own Across Our Calling. And so that's kind of the big picture question. That's some of the more sort of worldview laden questions to kind of frame this. But I want to explore perhaps a little bit narrower set of questions, including things like how well do our models, the models we make, describe the behavior and structure of created reality? What do they say about its fundamental nature? And how might this inform our understanding of God's providential, and I would say even playful, unfolding of creation through an untold number of, quote, let there be's, end quote, making new worlds. So this is what we continue to see today. And I'm going to really definitely be coming to you this as a scientist. And I'm going to stick to the science mostly, but I do want to have these questions in our minds. And I'm going to do so by, I'm going to sort of address these by thinking about three. This is the outline for the talk, brought to us by Kelvin. Let's go exploring. So first is thinking about scientific theory making and the formation of the moon via stochastic processes. I'll define this word stochastic in a moment. The creative role of these processes that we see expressed through the abundance and diversity of planets and worlds observed across thousands of planetary systems. And then finally close by extending this idea to a vast array of worlds without end that we see throughout the cosmos. And so that's where we will be going. Okay, so we're going to start not at the very, very beginning, but at a beginning and think about, how our planetary systems born. And by the way, if you see pictures, I do try to tell you what they are for context. This is the famous pillars of creation. This is an image taken by Hubble. This is a stellar nursery. It's where stars and new planetary systems are being born about 7,000 light years away. So we are witnessing this happening before our eyes today. So what is the story? Like, what is the scientific story of how these systems are made? And this is the sketch of modern planetary formation, the theory of protoplanetary disks and stars. So what's happening here? So basically, these stellar systems form out of a large molecular cloud that exists in the galaxy, mostly in the spiral arms of our galaxy. And what you're observing, or what you're seeing here on the top row, is this process of cooling and collapsing. So over time, these molecular clouds cool, they begin to collapse. As they collapse, they preserve angular momentum. They tend to develop a disk-like structure around the new star that is being born. Now, around the same, concurrent with this process is the formation of this so-called protoplanetary disk that surrounds the star that is in the process of being born. The upshot of all of that is that planetary systems are born along with their stars. And so our solar system was born along with the birth of our sun. And it is thought that our own sun, our own solar system looks like it was born via something like this process. And this is what gives us this structure that we see in the present day solar system. Now, interestingly, we mentioned that word stochastic. This type of process is best described by stochastic models. If we try to simulate this sort of process, say in a computer simulation, the best way that we can do that seems to be these stochastic models where you run many runs starting with the same, many simulations starting with the same initial conditions, and you can actually get different outcomes each time you press go on the simulation. So it's an interesting feature and one that we will be discussing a little bit further on in the talk. You know, what do we do with this sort of behavior that seems to have such a strong component of statistical probability sort of built into the system, built into reality? We're going to first, though, start with a subset of this. So if you see this little section here, this is sort of like, let's zoom in and see what's happening to planets. And here we have these little planetesimals, and they sort of slowly accrete and collide into each other to build up larger and larger planetesimals until eventually we can get something like formations of the moon and the other planets that we see. So this is sort of a subset of the process zoomed in on one planet. So we're going to start with the moon and then work our way out. And I forgot to mention, but if you look at this slide, you may have noticed that there is a zoom out here as we start with the solar system, then move beyond our solar system to sort of our local neighborhood in this part of the galaxy, and then to the rest of the universe as we can observe it. Okay, so let's start with the moon. And the moon is fascinating for a whole host of reasons. And it has been, an object of human interest for millennia. And if we think about it, it's probably the object that we've spent more time staring at in the sky than any other object, I hope, because the other big choice is the sun. And so we have likely looked at the face of the moon more than any other celestial object, right? And so we see this in these artifacts like the Nebra disk. It is appointed in scripture as, it plays a role. It's a created thing that plays a role to help set dates and times. So it is the basis for the holy feast days, the schedule of the feast days in ancient Israel. And, it was seen as having this important role even before the time of Galileo. And after Galileo is really where we started seeing the moon as something that was subject to the same natural processes as the Earth. So before this time, there's more of this Ptolemaic view of the moon, that it belongs to the superlunary sphere. Beyond the moon is where we have sort of the divine, and then it's only here on Earth where natural processes occur. So it's really not until the 17th century that people started to think seriously about the moon as a natural object that would have a natural history in some way. And so we can ask the question, how do you make a moon? How did it get there? It's amazing, it's there, but how did this happen, right? Yeah.
Is this drawn in 1647?
The only things drawn in, IKEA is timeless. The only thing drawn in 1647 is this sketch at Velius. And so, just the disc itself is from 1647 there. So we can ask, and can we come up with a story for how the moon may have been made? And to do so, we need to develop some sort of model, some way of describing this sort of process. This is a picture of a model along with some lunar imagery taken by a satellite. And the one on the left there is actually constructed in 1874 by Naismith and Carpenter, and it's really quite remarkable. Now, the way that they did this is they actually made a model of the moon using plaster. So they sculpted a plaster surface of these craters, and then they set it at a low sun angle so they would get nice shadows, and they took a picture of it. It's a really quite remarkable model of the moon. And sort of using this as, how do we, the question, how do we assess models? And perhaps the simplest test of a good model is, does it actually reflect the real moon that we have, right? Does our story about the world actually in some way reflect genuine insights into created reality? In other words, we can't just come up with any story, right? It has to conform somehow, in some way, in some meaningful way, to what we observe in creation. So it is tethered, it must be tethered to created reality if it's going to reflect genuine insight in any meaningful way. So how do we assess this? Well, we have to turn to the evidence, right? So we have to stack up the evidence and see whether or not our model fits the constraints that are set before it. So we can start thinking about what are the properties of the moon. And this is a picture of the moon, which you've probably not seen before. And that's because this is the far side of the moon, right? Not the dark side of the moon, the far side of the moon. So this is the part of the moon that is always faced away from the Earth. Of course, more familiarly, we have this side of the moon, which is facing toward us. This is the near side of the moon. The moon's about 1% of the mass of the Earth, about a quarter of the Earth's size, physical size. Orbits at about 60 Earth radii, and one revolution takes 27 Earth days, which is the same as one rotation, and that's why the moon always keeps its same face toward us, right? So it's always facing us, keeping this face toward us. That's not an accident. It has to do with tidal forces. And we can start thinking about, what do we do with this? Now, if you're wondering what this means for scale, there you go. That's Iowa. That's, now you know intuitively how big the moon is. There's Ontario, right? And I did use the website where you make sure things are scaled correctly. So that should be the correct size of Ontario. Okay. I think this slide took me longer than most of the slides. Okay, so what are some of the other evidences? And this is, kind of getting to the heart of the observational scientific evidence. So the moon is less dense than the Earth. It contains less metal than the Earth. In fact, the moon as a whole kind of looks like the rocky part of the Earth in terms of its density. That's interesting. That's a constraint. Our story has to fit that. The moon-Earth system has high angular momentum. That has to do with its rotational energy. The moon is actually quite large for a planet our size. We in some ways have no business having such a large satellite. The other planets with satellites anywhere near this size are Jupiter and Saturn. So we're hanging out with some pretty good company there. But the Earth-Moon system is a very high angular momentum system. And the moon's orbit is gradually getting bigger. The moon is slowly drifting away from us at about 1.5, sorry, that's in inches per year. Multiplied by 2.54 for centimeters. Okay, so these are some of the constraints, just some of the constraints that we have to work with. And so different stories have been and had been proposed to match this. So things like the fission hypothesis. Maybe the moon was spinning so fast that it broke off thank you. The Earth was spinning so fast that it broke off a piece of the moon. Maybe they just formed together. So we talked about, I briefly mentioned this sort of accretion out of a disk. The planets are sort of born out of this disk of debris. Maybe the moon just formed by co-accretion next to the Earth. Or maybe the moon formed somewhere else and was captured by the Earth from gravitational interactions. And these were sort of the three big ideas that had been proposed earlier on in lunar science. And they all have, in some way at least, a fatal flaw in terms of matching up with the observational evidence. Fission hypothesis, that's actually too much angular momentum in the system. Co-accretion doesn't really make sense from a chemical standpoint and the bulk density differences. And capture doesn't make sense also for chemical reasons. And where would the moon have formed then if it didn't form near the Earth? So all of these had issues. And so there was no embrace of any one theory. And it kind of leads to what Kuhn would call sort of this crisis of paradigm. And basically, you know, one of the solutions is collect more data. More data is needed to tell a better story. And I wish I could tell you that this is the only reason why Apollo went to the moon. But what's another way that we could figure this out? Well, go get some samples, right? And so these are the Apollo missions starting in the 1960s. This is Apollo 17 with Jack Schmitt, who is actually a geologist. All of the other Apollo astronauts were astronauts that they gave a geology class to, and he was a geologist that they gave a astronaut class to. And so he collected, the other Apollo astronauts did a great job of collecting samples as well. But go collect more data, go get some samples from the moon. What does this actually look like? You know, if we can take a look at the moon, bring it into the lab, take a piece of the moon to the lab, what do we find? We find a couple interesting things. So the moon has sort of this interesting type of chemistry because on one hand, the Earth and the moon look like they're made of the same material or material that has been mixed very well. So this is a plot. It is a log-log plot, so it is a straight line, but I wanted to show every element on here, right? And so on the y-axis is the moon, and the x-axis is the Earth, and you can see that there is a general similarity in the overall chemistry and the composition of the moon. Now, that's interesting because it suggests that there is some common origin there. But at the same time, the lunar material appears to have had experienced a much more violent history. Right? And so I've highlighted there some of the elements which are in green. And I know it's kind of small print there, but if you look carefully at those elements, those tend to be elements that are more readily vaporized. They're more volatile. It's easier to lose them to space or into the gas phase. And if you look at the Earth and the moon, it looks like the moon is a little bit depleted in those types of elements. And we see some other evidence from isotopic systems. And so all of this is suggesting that there was some high energy event that the lunar material went through that the Earth has not retained in the Earth record. And so this is the origin of the giant impact hypothesis. So what's going on here? This is an artist's impression. It's not a photograph. But near the end of the Earth's own formation, near the end of the Earth's own accretion, there's this collision of a planet-sized object with the Earth, a planet-sized impactor hitting the target, in the Guild parlance, the Earth. And out of this debris, the moon is born. This is the giant impact hypothesis. First adopted in 1985 is sort of when it achieved sort of widespread adoption after a conference on the Apollo samples and reassessing at that point in time, where are these theories of origin for the moon? And what can we say now that we have these Apollo samples? And so I've got a video to show what this looks like in a simulation. This is not like canon, but a lot of the community calls the impactor Theia, which is, I believe, a goddess that is like the mother of Selene. So the names work out there. And so this is the impactor that comes in and strikes the Earth. Yeah.
First of all, I think she was a Titan. But so do they believe that Theia impacted the Earth on the same plane, or like slightly off kilter?
Different models say different things. Probably not direct. It would have been something probably more like a glancing blow, if I can get this to play. So here's a numerical simulation. And I should note there are many variations on this theme. In fact, you could go so far as to say that this is now currently the paradigm for lunar formation, right? So the main arguments, the main disagreements now in the field of lunar formation hypotheses are the conditions of the impact. How big was Theia compared to the Earth? What was the angle? How much energy? What was the spin rate, et cetera, right? So the idea here is that there's this collision. It forms this disk of debris. We're kind of flying around the Earth as this is happening with the camera angle here. And then that debris will collect and form the moon over time, right? And so we can look at this from a side view in another simulation. So what happens after the impact? We have this post-impact accretion step. And this is kind of an interesting plot to read, I realize. So now we are looking edge on at the system where this is the Earth. It's surrounded by this magma disk, almost sort of Saturn-like, this disk of molten debris and gas. And out beyond this boundary, this is the Roche limit. It's a tidal limit. Beyond that limit, things can start clumping together better. Beyond that limit, we start to see the formation of the moon via the accretion of all these little moonlets that form at the edge of that disk. So I can march that forward. So you see the big moon forms like right away, very quickly. And then over like the next millennia, we start adding more of this material onto the moon. I'll let that play out. And then it starts to migrate outward.
So this is literally only hundreds of years?
In this simulation, after the impact, it is thought that the accretion was pretty rapid. You end up with basically 95% of the moon after a millennia in this simulation. So this is one way we can build the moon through this sort of model. And this is sort of, again, artistic compression, looking at the Earth-Moon system following the impact. And, this is quite a story. It's kind of remarkable, but this is today really the paradigm for this event, right? And it's a story of some violence. It suggests that acts of creation are perhaps not safe, even if they're good. This is what we see. This is what the evidence seems to point to. Now, is this actually exactly the way it happened? That's still, we're still trying to figure that out. But this does do the best job of meeting a lot of these constraints. This does fit these constraints of angular momentum, and chemistry, and density, some of the other observations that we see when we look at the moon. Now, I mentioned this word stochastic. It's also this very stochastic process. The Earth built up over time from an immense number of individual collisions, and it produces this, the end of that process, this one very large collision. And it's something that has left us with a habitable Earth and an Earth-Moon system that gives us the tides and this object that marks the seasons and the days. Did it arise like this? Is this the creation mode for the moon? And that's just our moon, right? So I'm going to zoom out. We've made the moon, a moon. I don't know if it's the moon, but we've made a moon, right? And this is the story of how it was made until a better one comes along. Yeah.
Is it true that people also believe that Venus and Uranus were also impacted in a similar way? And that's how they explain why Venus spins so slowly and
Yes.
Uranus is on its side?
Yeah, so giant impacts seem to be a feature of the early solar system, which may have knocked like Uranus on its side. Venus has an unusual rotation. Yeah, good question. Okay, so that's just the moon, right? Now we're gonna kind of zoom out further. And it's thought that this type of formation event is a subset of a broader story of formation of the solar system, the gradual accretion of gas, dust, along with thousands and millions of planetesimals and eventually the planets themselves. And this goes back all the way to the theories of Swedenborg and Laplace, who famously, when asked by Napoleon about God's role, said, quote, "I have no need of that hypothesis." And so there's an interesting history here about how the Laplacian theory was received. Interestingly, it was actually sort of embraced by Christians in the United States at the time as sort of giving wonder to creation and the process by which God would have made the solar system. Because one of the features that this produces is a solar system that is in this nice planar, circular orbits, kind of all in one disk together. And before this time, that was seen as just completely remarkable. What are the odds of this sort of thing just happening on its own? But now in the modern theory, this suggests that that is actually just part of the process. That's part of the, the lawfulness we see expressing itself in creation. And moreover, we're starting to observe more and more examples of this type of process in these protoplanetary structures. So again, these protoplanetary structures are essentially capturing a solar system in the act of being created. This is a let there be live before our eyes, and we see these clouds of dust and gas around these stars that are being born. Here again, now we're looking at the Orion Nebula. This is about 1,300 light years away. And we see these structures in even more detail with some new observations that show the same sorts of orbital behaviors that were once cited as evidence for design. And so, here what we're looking at is this is an image of a protoplanetary disk. This one's about 450 light years away. The star that's being born is somewhere there in the center. And then around it, you can start to see these tracks opening up in the disk where it's thought that there might be planets there that are collecting material as they're being made, as they're being born. Right? So we're capturing this in the act. And, how do we model this? And what are the ways, what do I mean when I say that these are stochastic events? And again, stochastic processes are processes in which the same initial conditions can yield significantly divergent results. And that's shown here. And these are some models of building planetary systems. So there are simulations. There are researchers that do this sort of thing all the time. Basically run simulations of planetary formation and run it many, many, many times. And what do you get? What are the outputs? What kind of solar system, what kind of planetary system do you build each time you run the model? And they find that you can get much different types of variations in planetary size, planetary orbits, the spacings, how many planets do you get? A wide array of planetary diversity. Question?
Is that JavaScript?
I have no idea. That's not my study. But this is Hoffman et al. So then that's the name of the paper, Stochastic Accretion of the Terrestrial Planets. Good question. I don't know. Okay, so what do we do with this stochastic behavior? And raising this as a possible way to question or a way to think about this in this way, that some sort of stochastic lawfulness can perhaps unexpectedly be thought of as the condition of freedom. And what I'm getting at here is this is where the laws are obeyed at the very particular or fundamental level of creation. But the laws being obeyed in each of these individual tiny little steps, which seem so inconsequential, are the very things that are giving rise to this very wide range of outcomes that we observe. It is the lawful faithfulness of creation that is giving rise to this beautiful diversity in planetary structure. The very lawfulness of creation giving rise to the diversity of the worlds that we observe. And what does that give us, right? Well, it gives us this, for example, right? So we'll treat this as our norm. This is our solar system. We have a range of planets here. We have the so-called terrestrial planets. We are on one. These are the rocky worlds. In the inner part of the solar system, we have the so-called gas giants. In the outer part of the solar system, here we see a diversity already of different types of planets, rocky planets, gas giants, ice giants, a few other things as well, including the planet Pluto and its moon Charon. Pluto's a planet, I think. I will use the geophysical definition of a planet, and that is if its hydrostatic equilibrium has overcome its mechanical strength, right? What I mean by that is if it's round, then it's a planet, right? And that's fine, right? We have many rivers, and that's fine. You remember the big ones, and you remember the ones that you live near. Planets can be thought of in the same way. It's a little soapbox. Now I'll step off of that. But this is in our own solar system. What else do we see? So this is now a sort of a new quiet, in some ways, a quiet revolution that we're seeing in the sciences and in astronomy, as we have now discovered many, many, many other planets around other stars, these exoplanetary systems. So these are planets that are orbiting stars other than our sun elsewhere in our galaxy. Yeah, question.
Is Ceres a planet? It's round.
It could be considered a planet by this definition. Yeah, so yeah, you have to, if you let Pluto in, you have to let some other things in too. That's okay. That's okay. Okay, so this is the population of exoplanets. And the first few were discovered in the early and mid 1990s, and we now, as of a week or a month ago or so, over 6,000 known planets outside of our solar system. Mostly detected by radial velocity. This is where you look for little wobbles in the star that the planet is orbiting, or by transit. That's if you, the big purple bars there are transits. That's if you see that planet pass in front of its star and you see a little dip in the starlight telling you that that planet is there. Right? So we know of over 6,000 confirmed exoplanets in our galaxy. On the right-hand side is showing mass and orbits. If you are wondering, it is very small, but here is Earth for reference, right? Here is Jupiter. So you can see so far, we have a bias toward very large planets that are close to their star, right? Those are easiest to see. They're bigger and they create more of an effect in terms of their observation. It's easier for them to block their star from our perspective. They will also create a bigger wobble in the light coming from that star if they're more massive. And so this, we are searching. There is this search for some other Earth-like planet. But you can see one of the challenges so far is we are mostly seeing the big planets that are close in. Right? And what kind of systems do we see? So we can walk through some of these things. Like, for example, if we think about individual planetary systems, how many planets do we detect, have we detected so far per planetary system? So most of the planets we've seen so far are the only planet that we've detected around that star. So how many planets are in that system? Well, just one that we've detected. And here's the solar system. There's 8 detected, at least 8 planets detected in our own solar system, right? We also see some other interesting types. How many stars per planetary system are there? Well, most of them, as far as we have observed, and in our own, we just have one star that we're orbiting, that's the sun. But there are quite a few planetary systems that have 2 stars. And so that's this example, right? So there's Tatooine. So we do have planetary systems of this type, right? We are discovering this diversity of different planetary types. And taking that even further, what can you make a planet out of? Right? What are the ingredients of a planet? I've told you I was going to tell you about how to make a planet. Maybe I did. I am now. How do you make a planet? Well, there's basically 4 ingredients, right? When it comes down to it, and I'm not trying to go back to some Greek conception of planethood here, but basically 4 ingredients: metals, rocks, ices, gases, right? And depending on the relative proportions that you use, you can make about any type of planet you could want, right? This is the materials that we have in creation. And so here again, we see this sort of very creative interplay between chance and law, right? This lawfulness expressing itself in this sort of freedom of diversity based on that faithful structure embedded in created reality. And we can point to many analogs found in the gifts of everyday life: flour, water, salt, yeast. How many different types of bread can you make? Water, barley, yeast, hops. How many different permutations exist from those 4 ingredients? So out of this sort of simplicity and lawfulness emerges this beautiful expression of diversity. Yeah, question.
Have we figured out what Trust 2B is made out of? That's the pitch black one.
No, not as far as I know.
Then why
That's
not?
still.
It's like gaseous asphalt.
What's that?
Is it gaseous asphalt?
I am not sure.
Okay.
I don't know if it's conclusive yet.
You know about that one, right?
Yes.
Okay.
Yeah. Okay, what else do we see? Right? What kinds of planets do we see? So that's the ingredients. Like I can make these different types of planets. Well, how much do we actually end up with of each category? Now, again, here we are seeing something to be paying attention to. Our bias is showing here because we are more readily able to observe the large planets, the planets that are closer in. But this is what we see so far. A lot of gas giants, sort of Jupiter and Saturn-like, a lot of Neptune-like planets. This was a surprise. It looks like that is actually a very common kind of planet. Who would have known? We didn't know that, right? Until the advent of exoplanets. And then, of course, this lovely category called super Earths. So these are rocky planets of unusual size. And then finally, the terrestrial planets, things like Earth and Mars, et cetera. So this is the observed distribution. And not only do we see all these different types of planets in terms of their overall composition, we also see a great diversity in the processes occurring on these planets and things like the chemistry, the different types of clouds that can form. And so this is kind of getting a little bit more into some of my own research, thinking about cloud formation in exoplanets, where we don't not only have just water clouds like on the Earth, but we have clouds made of rock, clouds made of iron and silicates and sulfides and other minerals deep in these planets. And now, thanks to observations from platforms such as James Webb, we're actually starting to see evidence for some of this unusual chemistry in the atmospheres of the planets. We can actually look at the weather in some of these planets where it might be cloudy with a chance of metal rain in the interiors of some of these planets. So we see diversity there as well. And we can also even sort of think about this as in a Goldilocks sort of way. I will admit I took this slide from a library talk that I gave to you middle schoolers, because I like to ask them, like, which of these planets would you like to live on, right? Is it too hot? Is it too cold? Or is it just right? Where can humans flourish? And here too, a remarkable diversity, not only in the type of the planet, but in the intro there, I think I just mentioned every nook and cranny, and every planetary world that we see is full of nooks and crannies. There's really a breathtaking degree of intricacy here, down to the smallest pebble. At the very limits of the resolution of creation itself, every nook and cranny of every world. Just think of all the places that exist in all of these worlds, right? It's incomprehensible, and it's an extravagance that's just beyond our comprehension. Yeah.
Is it true that people believe Core 7b to formerly have been a gas giant that the sun blasted all the atmosphere off?
Yes, most likely. It's too close for comfort to its star, definitely. Yeah.
How fast do you think that happened?
I don't know. That's a good question. I'm sure
there's another planet, Osiris, that's also having the same thing happen.
Yeah. So if these things get too close to their sun, interesting things happen. Right, so we're going to go even further out now. We're going to zoom out even further. So far, I've been keeping us inside this circle. Right, this is our own Milky Way galaxy. Estimates are that it's about 100,000 light years across. And here, the UR here is here. And this circle goes out about 3,000 light years radius. And so pretty much all of these 6,000 planets that we discovered, almost all of them are found somewhere inside this circle. Right? Very, very, very close, just a few thousand light years. Right? Very close. Right? Okay. And now, recent studies suggest, and this is just snippets of some of these, recent studies suggest that planets actually outnumber stars. So in a place like our Milky Way galaxy, which probably contains on the order of about 100 billion stars, it is now, 6,000, that's nothing. It now seems like as if there's more planets than stars, more of these worlds that we're discovering. The analogy here, we don't have black squirrels in Iowa. You do, I've learned, right? And so, if you shine a flashlight in one part of the dark room, can you make inferences about the rest of the room, right? I've seen already today like 2 black squirrels just walking from across the street to here, right? There must be a lot of black squirrels in Hamilton.
We can send you 50 from our.
Right? So you see the connection here, right? We look in this one small patch of sky or the universe, thousands of planets. How many must there then be throughout the rest of the cosmos? So we'll zoom out even further. What about things on the galactic scale? This is M101, beautiful world galaxy. And we're going to take a look from Hubble here. And so Hubble set out to sort of map, how many, we can ask the question, how many galaxies are there? And so Hubble performed this experiment. This is called the Hubble Ultra Deep Field. And Hubble stared at one tiny little patch of the sky, about that size, right? Compared to the moon. And the moon's back. Well, how big is that? Well, here we go. How big is this? Well, this whole slide covers about a square inch, but he didn't say square inch, right? Yeah, 1 thumb's width, right? So go ahead and hold out your thumb. Yeah, now this is where I ask, what did you think of the talk? If you hold out your thumb, you can kind of compare, how big are objects. So this whole slide would cover about 1 thumb's width, right? You can also do like a parallax thing if you wink at your thumb back and forth. So if you go outside tonight and you hold your thumb up to the sky, you will see that the moon will probably take up, about 1/3 or so of your thumb width, right? That's about 2 degrees of angular arc. And you may say, well, my thumbs are wide, well, maybe your arm's long then. It works out pretty well for humans. Humans are sort of self-correcting in this mode of measurement, right? So this is just one thumb's width, right? And we're looking at, now imagine that. If this whole thing is the width of your thumb, now you're looking at this tiny little speck. And so what did Hubble do? Hubble stared at this for a total exposure time of 1 million seconds. Okay, hold still, galaxies. 1 million second exposure. This is 1/13 millionth of the whole sky. We're zooming in. And this is what it saw. Right? There are over 10,000 galaxies in this one view. Every square inch. What does every square inch mean? In 10,000 galaxies, in just this little sliver, less than a thumb's width. As many, so that, we extend this, we can do some math on this. There's as many as 1 trillion galaxies. Each of those typically contains on the order of 100 billion stars. So there's something like 100 billion trillion stars in the observable universe. And more likely, there's even more planets than that in the observable universe. The stars outnumber planets. So what is worlds without end? This is worlds without end. Truly. How do we exhaust this? We can't. This is beyond our comprehension. And so I can't really express it. Can't package it. I'm gonna use it, so what do you do? Then you turn to a Chesterton quote. And I've changed this slightly, and I think you'll forgive me that. I've changed daisies to stars. But I'm gonna go ahead and read this, which I think we'll get at. Part of what I'm saying here, the monotony of the everyday, of the particular, the fundamental, but expressed in a way that gives us great beauty and diversity throughout creation. So because children have abounding vitality, because they are in spirit fierce and free, therefore they want things repeated and unchanged. They always say, do it again. And the grown-up person does it again until he is nearly dead. I've spotted the parents in them. For the grown-up people are not strong enough to exalt in monotony, but perhaps God is strong enough to exalt in monotony. It is possible that God says every morning, do it again to the sun, and every evening, do it again to the moon. It may not be automatic necessity that makes all stars, planets, or worlds alike. It may be that God makes every star separately, but has never got tired making them. So I will leave you with that, and I'm happy to answer any questions that you may have. Thank you.